Okay, I can start now. Well, good afternoon to everybody. I'm sorry we are a little bit late, just 3 minutes or so, but we're just getting to get used to this technology. I'm Gracinda Gomes from the University of Lisbon, and it is my pleasure to introduce you to Peter Camera this afternoon. Well, I'd like to say a few words about Peter, and I shall start from the beginning. And the beginning is Peter was born in the garden city of Queensland in Australia. And since he was a little boy, he loved to count. And I remember him telling me that he used to count everything he could encounter. And so his love of mathematics appeared and he developed it. And from that inland city in Australia, he became a mathematician of the world. In his career, Peter has been interested in many areas of mathematics, in particular in algebra and combinatorics, and also in model theory, but not just. Next to him is one of his collaborators who works in statistics. Well, in his career, Peter has been a professor in various places, and I'll just mention a couple, in fact, 3 of them. He was a professor in Oxford, and then for many years, he was a professor in Queen Mary in London, from where he retired, and is nowadays an emeritus professor. But he's at the moment in St Andrews in Scotland, a place very dear to all of us, people from Semigroups. But Peter has taught courses and seminars and all sorts in many places in the world, and in particular in Portugal. And I dare to say that Portugal has a special connection and a special relationship with Peter. And particularly between, we take in account the work of João and Peter together and as collaborators. But speaking about Peter, we have to speak about numbers. We must count. And as we must count, I would like to tell you that he has well over 300 papers, 12 books, almost 200 co-authors, including Erdos, and an amazing number of students. He has an enormous impact in mathematics, and I could see that I could count at least 40 PhD students. So this is a bit of Peter's story or history, and I'd like to conclude by also mentioning that Peter has got various prestigious prizes for his outstanding research and for his qualities of teaching. I'll just mention the Whitehead prizes, both senior and junior, and only 3 people have got these 2 prizes together, and Peter is one of them. So Peter, it will be a great pleasure to listen to you this afternoon, telling us about conversations between groups and graphs.
Thank you very much, Gracinda. Well, I really do wish that I could be with you in Portugal. As you said, it does hold a special place for me. Looking at this picture on my first slide makes me really, really want to be there with you. And I just wish it could happen and will happen again soon. Anyway, I'm going to talk about groups and graphs, 2 of my favorite topics, but 2 rather contrasting topics. So they represent rather different parts of the mathematical universe. So groups measure symmetry, as everybody knows. They're highly structured, elegant objects, whereas graphs are much wilder. You can put in edges however you please. There are no restrictions. Some graphs are beautiful. Most are, let's say, a bit scruffy. Well, there's nothing wrong with that, as you can see from the picture. But it does mean that these are 2 rather different topics, and yet they have a lot to say to one another, as we shall see. I'm going to describe to you several areas where groups and graphs have had a very productive conversation. But first of all, just a little bit about the 2 topics. First of all, I said graphs are scruffy. I'm thinking of finite graphs, but some of them are beautiful. Here's a a rare example. This is the famous Peterson graph. And if you want a definition of it, if you're not a graph theorist, you take the dodecahedron, think of it embedded in the sphere. Then if you quotient out the sphere by the antipodal relation, you get the real projective plane, and the dodecahedron skeleton collapses down to the Peterson graph. So there it is embedded in the real projective plane. Groups are much more tightly structured. We know all the finite simple groups, and according to the theorem of Jordan and Holder, any finite group is constructed from finite simple groups by an extension process. But the extension process is still a little mysterious, but at least we can estimate fairly accurately the number of groups of order n, and the most prolific values of n are prime powers, and the number of groups of order p to the n is roughly p to the 227th n cubed. So a strange constant there, 227ths, but that counts the groups. As we'll see, in the infinite case, there are more subtleties. There's a more nuanced relationship between groups and graphs, but that's the finite case. Infinite groups are a very different matter. There is no notion of a typical infinite group. There is no classification of groups. In order to study them at all, we have to impose some kind of a finiteness condition. They may be finitely generated or presented, locally finite, pro-finite, finite cohomological dimension, etc., etc. There's always a finiteness condition lurking somewhere in the background. So infinite groups are much more mysterious than finite ones. In the case of graphs, well, you can draw a graph any way you like, and almost certainly it will have no symmetry. And indeed, symmetry is somehow biased against in the study of graphs, and yet there are enough symmetric graphs that it's really important to look at that. But strangely enough, when you go to the infinite, you would expect things to be much worse, but in fact, almost all countably infinite graphs have a huge amount of symmetry. And I'm not going to say very much about this. I did talk to the Portuguese Mathematical Society about this famous graph R a few years ago. If you choose edges independently with probability half, so if you choose a random graph on a countably infinite vertex set, it's almost surely isomorphic to R. And also, if you're like topology rather than probability, there's a complete metric space structure on the set of graphs, and a co-meager subset of the graphs are isomorphic to R. So it is the typical countable graph, and that's something that doesn't exist for groups. Anyway, so on to the first conversation. I mentioned, one reason for mentioning this now is some of you may have been at Wolfram Benzer's talk this morning. He mentioned something rather mysterious that happens on 100 points in this connection with this question about the existential transversal property. Well, this is the history of it. So on a very special day, 3rd of September 1967, Donald Higman and Charles Sims were at a group theory conference in Oxford, and Marshall Hall had just announced the construction of a simple group, Yanko's second group, which was a permutation group acting on 100 points. And Higman and Sims got to chatting over the conference dinner, and they wondered whether there might be another sporadic simple group also acting on 100 points. And amazingly enough, such were the times, by the end of the evening, they'd actually found one. This proliferation of sporadic groups didn't go on for very long, but it was very exciting while it happened. So I'll just briefly take you through the construction. It depends on a certain configuration, a certain design that was first constructed, I think, in 1931 by Carmichael and proved unique by Witt. Witt gave essentially the first rigorous construction of the Mathieu sporadic groups. Anyway, this configuration has 22 points and 77 blocks. And its automorphism group contains the natural group M22 as a subgroup of index 2. So Higden and Sims did the following. They said, take the points and the blocks of the configuration as vertices, that's 99, and one more to make 100, which I'll denote by this asterisk. And there are only 3 simple rules for the edges. The asterisk is joined to all the points, all the 22 points. A point and a block are joined precisely if they are incident in the configuration, if the point is contained in the block. Any point is joined to the asterisk, and it also lies in 21 blocks, so that gives it 22 neighbors also. 2 blocks are joined if and only if they're disjoint as sets of points, so no point is incident to both. And any block has 6 points and has 16 blocks disjoint from it, and again 6 and 16 make 22. So every vertex of this graph lies on 22 edges, and using the results of this essentially, they were able to show that the graph really looks the same from any point. So any point can be taken to any other point by an automorphism of the graph, and as a result they were able to work out the automorphism group, and they found that it acts transitively and has a new simple group, and a then new simple group as a subgroup of index 2, and that's the Higden-Sims group. And if you were at Wolfram's talk, the full automorphism group and its subgroup of index 2 were those 2 strange examples of degree 100 that he mentioned in his talk. Okay, so I can't let that pass without a historical note. It turns out that Dale Mesner had constructed this graph more than 10 years earlier. He worked in combinatorics and statistics and knew nothing about group theory. He'd been defining a class of graphs that he called negative Latin square graphs. It wasn't clear that they existed, so he laboriously constructed this graph as an example. Because he wasn't a group theorist, he wasn't able to use the work of Carmichael and Witt, which would have made his job a lot easier, and he didn't think to consider the automorphism group of the graph. But the graph was definitely first discovered by Mesner. Not the first time that this has happened in mathematics, or the last, no doubt. So that's the Higden-Sims graph. That is the simplest construction of a sporadic simple group, I believe. So, on to counting. Bricinda mentioned my love of counting. If you haven't read this book by Richard Brautinger, The Hawkline Monster, subtitled A Gothic Western, it's worth a look. One of the heroes is a gunslinger called Cameron, and his trademark is that he counts things. And that really, really annoys some of his friends and colleagues. But in the end, it's his counting that saves the day for the heroes. And so he says at some point in the book, I count a lot of things that there's no need to count, just because that's the way I am. But I count all the things that need to be counted. So I'm going to do a little bit of counting for the second conversation. So let's look at the Peterson graph again. There it is, beautiful symmetric graph. And we're going to color it, color the vertices. And we'll take the usual rules for graph coloring. That is, we're not allowed to give the same color to 2 vertices that are joined by an edge. And you might be interested in how many different ways can you color that graph if you're given a set of, say, Q colors available to you to color it with. How many different colorings does it have? Well, this question, how many colorings, was first looked at by Birkhoff. The answer turns out to be a polynomial in Q, a monic polynomial with degree equal to the number of vertices. And this is called the chromatic polynomial of the graph. So the colorings are counted by the chromatic polynomial. And you might think that was the end of the story. Birkhoff introduced the chromatic polynomial as a tool. He was attempting to prove the four-color conjecture, that a graph that can be drawn in the plane without crossings can be colored with four colors. And so he introduced this polynomial and thought that if he could prove that the chromatic polynomial of a planar graph doesn't have 4 as a root, that would mean that if you plug in 4, you count the number of colors and it would be non-zero, and therefore the graph would have a coloring with 4 colors. So that was his idea. And of course, it didn't actually work out like that. And the 4-color conjecture was finally proved using rather different methods. But the chromatic polynomial has still been very influential. So just to take one small example of this, not very long ago, I don't recall exactly, Alan Sokal surprised a lot of people in the graph polynomials community. He proved that if you take chromatic polynomials of all graphs and look at their roots in the complex plane, their complex roots, these are dents in the entire complex plane. Now, Sokal was a physicist, and he was coming to this from the Li-Yang theory of phase transitions in the Potts model in statistical mechanics. You don't have to know anything about that because it exactly translates into this question of do the complex roots of chromatic polynomials approach the real line arbitrarily closely? Well, indeed they do. They're dense in the whole complex plane. That's what Sokal showed, which contradicted a fairly long-standing conjecture at the time. So let's go back to the Peterson graph. It's got 10 vertices, so its chromatic polynomial is a polynomial of degree 10. And a polynomial of degree 10 does grow quite rapidly. If you calculate the chromatic polynomial of the Peterson graph, which is not so hard to do, and plug in 10, you get this rather large number of colorings with 10 colors. So can we do that? Can we give any kind of structure to that set of colorings? And there is some practical motivation for doing that as well. One of the places that graph coloring is used in practice is radio frequency allocation. If you have some radio transmitters, if they're too close together, they mustn't be allocated the same frequency because they will interfere with one another. So if you imagine that you have a graph whose vertices are the sites of the transmitters and they're joined if they're sufficiently close that they would interfere, then you need a proper coloring of that graph. But you don't care what the colors are. You only need the partition into color classes. And that might be very much smaller than this large number we've got here. So can we find this? Well, the answer is yes, we can. Because after all, what do we have to do? We have this many, this 205, this large number of colorings with 10 colors. The first thing we'd like to do is figure out how many of them actually use all 10 colors. Obviously, not all of them do, because if you can color the graph with fewer than 10 colors, you could simply leave some colors unused. Now, combinatorialists will recognize immediately this is a job for the inclusion-exclusion principle. We know how many colorings using any subset of the total set of colors. And so from that, using inclusion-exclusion, we can count the number of colorings that really do use all the colors. And once we've got that, if there are q colors, we simply have to divide the answer by q factorial to get the number of partitions. So this is an easy computation. And once you've got the chromatic polynomial, you can easily write down a formula for this number of partitions. So what are these partitions? They're just partitions so that no edge is contained within a single part of the partition. So partitions into independent sets, as some people would say. Right, so that's one way that you can cut down the size of the space. Here's another. You can use symmetry. We've got groups hanging around, so let's put them to use. The Peterson graph has a lot of symmetry. Its automorphism group actually has order 120. It's isomorphic to the symmetric group S5, not in its action on 5 things, but there is a way of identifying the vertices of the Peterson graph with the 2-element subsets of the set 1, 2, 3, 4, 5. And so there are 5 choose 2, there's 10 of those. And the rule is you join 2 subsets if they're disjoint, just as we did in the Higman-Sims case. If you have 2 colorings such that some automorphism of the graph carries one to the other, then we don't really want to count them as separate. So we'd like to count colorings up to symmetry of the graph. Can we do that? Well, yes, there is another polynomial that does that job. This is the so-called orbital chromatic polynomial. So it's a polynomial whose value at Q is the number of orbits of a group of symmetries acting on the set of proper colorings of the graph. So it takes account of both the graph and the group of automorphisms. You can use the full automorphism group, but you don't have to. You can use a subgroup if that would be more convenient. So you put in these 2 things, the graph and the group, and you get a polynomial. Its degree is still the number of vertices, but the leading coefficient is 1 over the order of the group. So in the Peterson graph, this will be a polynomial of degree 10, but the leading coefficient will be 1 over 120. So we can cut the numbers down by quite a considerable factor by counting up to symmetry. Now, of course, I've given you 2 ways of cutting down the size of the space. What if you want to combine the 2? So you want to count not proper colorings, but color partitions, and you want to count them up to the action of an automorphism group. Well, that's an open problem. I don't know a formula for that, for an arbitrary graph and group. I'd very much like to have one. I don't. And I'll give you the numbers for the Peterson graph in a minute so that you can see the effect of these reductions, but I don't have the formula. The numbers given here, I just worked out by essentially brute force computation. So these are the results for the Peterson graph. So the first row just evaluates the chromatic polynomial, and you see the numbers here. They grow like a polynomial of degree 10, which is fairly rapidly. In the second, we've applied the inclusion-exclusion principle and then divided by Q factorial to get the number of partitions of the graph into independent sets. And let me just pick out one to show you how it works. For 9, the answer is 30. Well, if you have a partition of 10 vertices into 9 parts, one part has size 2 and all the others have size 1. The parts of size 1 can't contain edges, but the part of size 2, you have to choose a non-edge for that. There are 30 non-edges, and that's why there are 30 partitions of this type. Now, the orbital chromatic polynomial works out like this. And at the right-hand end of the page, roughly speaking, these numbers have been divided by 120. But that's not true all the way along because some symmetries fix some colorings. And then if you combine the 2, so this is the orbits of the automorphism group on color partitions. And you see these numbers are much, much smaller. And I would argue that it's probably more meaningful to know that there are, up to symmetry, there are 36 partitions into 6 independent sets, rather than to know that there are 3 million proper colorings of the graph. Anyway, I would very much like to have a formula for that last row. Okay, so that's maybe a good point to stop and ask if anyone has any questions so far before we go on to the third conversation. Well, I don't hear any, so I will continue.
I don't see any.
Okay, I'll continue then, thanks. So the third conversation is work that I have been doing mostly in Portugal, mostly with João Araújo on synchronizing automata. So first I have to tell you a little bit about automata and semigroups before we get back to the graphs and groups. So an automaton is, think of it as a black box with some buttons on the outside. It has a set of internal states, and it can read symbols from an alphabet. So pressing the red button is like feeding in the symbol red to the machine. And all it does is read a symbol and change its state. And so I'll give you an illustration on the next slide, but let me just remark now that you can read one symbol, the machine can read one symbol and change its state, but it can read a sequence of symbols. Each symbol causes a state change, and so the effect of reading a word is to compose all these state changes that you've met along the way, and the final state will be the result of this composition of state changes. So an automaton is said to be synchronizing if there's some word which we call a reset word, such that if you feed that word into the automaton,
Peter, can I interrupt you just a second? Can you adjust your microphone?
Can I adjust my microphone?
Oh, you're fine. That's fine. It's just your position, probably.
Yes, so I'll just lean forward a bit.
That's okay.
Right. So a reset word means that if the automaton reads that word, it ends up in a known state, a fixed state, independent of where it started. So wherever you start, if you read a reset word, you end up in a position that only depends on the reset word, not on your initial state. And obviously this is useful if you have the machine and you want to bring it into a known state. You may want to take the back off to do a repair. Well, you want to put it into a safe state before you do that. So that's the reason for wanting a reset word, and so for wanting your automaton to be synchronizing. So here's an example. And you see this is a convenient way of representing these things by these colored directed graphs. This automaton has 4 states, which I've numbered 1, 2, 3, and 4. It has an alphabet of 2 letters, and the letters are the 2 colors, red and blue. So if it reads red, then it simply goes around this cycle one place anti-clockwise. If it reads blue, if it's in state 1, it goes to state 2, but if it's in any other state, it stays where it is. So those 2 transitions, this comprises an automaton. It is a synchronizing automaton. You can check that blue, 3 reds, blue, 3 reds, blue is a reset word. So let's just do one example. Suppose I start in state 3. Blue will leave me where I am. 3 reds will take me down to state 2. Blue will leave me where I am. 3 reds will take me to state 1, and blue will take me to state 2. And you can check that no matter where you start, this word will take you to state 2. So here's an infamous problem which has been open for over half a century now. Suppose you have an end-state automaton, and suppose you know that it's synchronizing. Prove that it has a reset word of length at most n-1 squared. Now you see here is a 4-state automaton, and the shortest reset word has length 3 squared, or 9. And if you replace this square here by a regular n-gon with the same 2 transitions, you will get an automaton which has n states and has shortest reset word of length n-1 squared. So this is best possible, but we don't know that it's an upper bound yet. And this is the famous Cherney conjecture, as I say, posed way back in the 1960s, still open. The best we have as a bound is a constant times n cubed in general. But I'm not going to talk about the Cherney conjecture here, let alone solve it. I want to go on to something a little different, because as it stands, what I've told you seems to have nothing to do with either graphs or groups, but they're about to appear. So semigroups will appear first. So you take your automaton, it reads a letter of the alphabet and it undergoes a transition, and we can think of that transition as a function from the set of states to itself, right? And remember that if we read a word, we simply compose the corresponding transitions. So all the possible transitions that you can get by reading words, everything that you get by closing this set of basic transitions under composition, including the identity map, because you're allowed to do nothing to read the empty word. And that will be a transformation monoid, in other words, a semigroup with identity on the set of states. So the elements of this monoid are transformations. But it's more than just a transformation monoid. It has a distinguished set of generators, namely the basic generators here. So the Cherney conjecture would say that if you have a transformation monoid which contains an element of rank 1, an element which collapses the whole of omega down to a single point, then you can write that as a product of at most n-1 squared of your distinguished generators. So that's the first transformation we make. So an automaton is essentially the same as a transformation monoid with a distinguished set of generators. Now I turn to graphs, and on the face of it, this seems to have nothing to do with what I was saying before. So if you've got a graph, it's got vertices and edges. An endomorphism is a map from the vertex set to itself that carries edges to edges. If it also carried non-edges to non-edges, and if it was invertible and its inverse had the same property, it would be an automorphism of the graph. But here we don't require that. The action on non-edges is not specified. So a non-edge could map to a non-edge, could map to an edge, or it could collapse to a single vertex. All possibilities are allowed for the action on a non-edge. So that's an endomorphism of the graph. And the endomorphisms of the graph form a transformation monoid. So what? Well, something nice happens, and this is, I believe, my main contribution to the theory of synchronizing automata. A transformation monoid is non-synchronizing if and only if there is, and I'll explain these terms in a moment, a non-trivial graph on the domain, the set of things that the monoid acts on, such that M is contained in the endomorphism monoid of gamma. And we can assume that the clique number and chromatic number of gamma are equal. So here are the explanations. The graph is trivial if it has either all possible edges or no edges at all. So we rule those two cases out. If you have all possible edges, then the only endomorphisms are automorphisms. If you have no edges, then every map is an endomorphism. So we leave those out. The clique number is the number of vertices in the largest complete subgraph. So the largest size of a set where all the vertices are joined. And the chromatic number is, in terms of proper colorings, as we were talking about before, the number of colors required to color the vertices so that adjacent vertices get different colors. Now, the clique number is always less than or equal to the chromatic number, because if I have m vertices, any two of them joined, then I need at least m colors just to color those m vertices. So that's the chromatic number. So we can take a graph with clique number equal to chromatic number, and a transformation monoid is non-synchronizing if and only if it's contained in the endomorphism monoid of such a graph. Okay, now, if you're a computer scientist or a complexity theorist, you're probably shaking your head in amazement at this point, because you know that clique number and chromatic number are hard to determine. Wouldn't it be easier to look directly at the automaton and decide whether it's synchronizing or not? Well, that's a good question, because in fact, there's a polynomial algorithm for deciding whether an automaton is synchronizing or not. But this is more general in the sense that it can deal with lots of monoids simultaneously, as you'll see in a moment. So now to groups. So a permutation group is, with one definition, it's a transformation monoid in which every element is a bijection. So every element has an inverse. Permutation groups are the oldest part of group theory. Galois would have understood a group to be a permutation group, and indeed so would almost everybody up until at least the middle of the 19th century. So permutation groups, this is, I became a mathematician thinking about permutation groups. So this is old territory to me. So a permutation group can't be synchronizing as a transformation monoid because every element is a bijection. So there's no element that will collapse everything down to a single point unless there's only one point in the domain. So you can't talk about a permutation group being synchronizing in the sense I define. So what we do is, as often in mathematics, we hijack the word, put it to a different use. So here's the definition of a synchronizing permutation group. Permutation group G, acting on the set omega, is synchronizing if whenever I take a transformation of omega which is not a permutation and see what G and F together generate, so I'm allowed to compose elements of G and F as often as I like, look at all the things I get in that way, they form a transformation monoid. This should always be synchronizing, no matter what F you choose, right? So permutation group is synchronizing if every transformation monoid that's obtained by adding one more element to one non-permutation to G is synchronizing. And from the theorem I just told you on the last slide, we get the following. A permutation group is non-synchronizing if and only if it is contained in the automorphism group of a non-trivial graph with clique number equal to chromatic number. So here in the automorphism group rather than the endomorphism monoid. So let me just remark that if you look at the endomorphism monoid of a graph that has at least one edge, it can't be synchronizing because you can never collapse that edge. So one way around, it's easy to see there's a connection between synchronization and graph endomorphisms. The other way is a little more work, but not particularly hard. Anyway, so there's the definition of a synchronizing permutation group. So which permutation groups are synchronizing? Well, we have a long-running project on this. It's not finished yet. So here's a quick summary of what we know. If you have a permutation group which is synchronizing, it must be transitive. That is, you must be able to map any point of omega to any other by an element of the group. Or to put it another way, no subset of omega apart from the whole of omega and the empty set could be fixed by the group G. So that's the first thing you can say. The second is that it must be primitive, which means that it fixes no partition of omega apart from the two trivial partitions, the partition into parts of size 1 and the partition that has the whole of omega as a single part. So let me just explain why imprimitive groups, groups that do preserve partitions, are not synchronizing. So you take a transitive but imprimitive group, it fixes a partition, and because of the transitivity, all the parts of that partition must have the same size k. So here's a very simple construction of a graph. Take the complete graph on each part of the partition with no edges between. That's invariant under the group, and its clique number and its chromatic number are both equal to the size of a part of the partition, to k. So the group is non-synchronizing. So synchronizing groups must be primitive. So they're a nice class of permutation groups that contain this class of great interest to group theory, the primitive permutation groups. And going on from there, the Onan-Scott theorem divides primitive groups into 4 types. There are, they go by the name, I won't explain these in detail, they go by the names affine, wreath product, diagonal, and almost simple. Now here, affine groups, let's do wreath products first. Wreath products preserve what coding theorists know as Hamming graphs. So you take all the words of a given length over a given alphabet, you join 2 of them if one change turns one into the other. And they have clique number equal to chromatic number. So the groups that preserve them are non-synchronizing. For all the other 3 types, you can have synchronizing and non-synchronizing groups. But very recently, we were able to make a considerable advance in the case of diagonal groups that a diagonal group that has, so the ones that are where that there's a normal subgroup, which is just a direct product of two groups, two simple groups, may be synchronizing, but if there are more than two factors, they're definitely non-synchronizing. So that was the most recent big development. I think I'll skip this slide because time is running a little short. So I want to get on to graphs on groups, which is my recent main interest, I suppose. So there are several types of graphs that live on a group. So the vertex set is the set of group elements, and the graph is supposed to tell us something about the group. And there are really two main types. The first type are Cayley graphs. Cayley graphs are graphs for which the vertex set is G, and the right translations by elements of the group are automorphisms of the graph. And just a very brief comment. This is a huge topic. Algebraic graph theory is not entirely, but largely about Cayley graphs for finite groups. Geometric group theory, which is a very important topic these days, is about Cayley graphs for finitely generated infinite groups. So the idea goes back to Cayley in the 19th century. He showed that every group could be regarded as a permutation group because of this action on itself, and this action preserves these graphs. So I think I won't say any more about that. I'll go on to the other type, which are the ones that are not invariant by the group acting by translation, but by the automorphism group of the group acting in the natural way on the group itself. So the prototype example of one of these is the commuting graph of a group. So you take the vertex set to be the whole of G. You join two elements x and y if they commute, if xy is equal to yx. And this first appeared in a paper of Brouwer and Fowler in 1955. With hindsight, this was the first step on the long journey to the classification of the finite simple groups. But there are two odd things about that paper. First of all, the theorem that it's mostly remembered for these days is the theorem that says that any given group can only be the centralizer of an involution in a finite number of finite simple groups. And that led to the project of classifying groups by the centralizer of an involution. Brouwer and Fowler don't state that explicitly as a theorem. They simply mention it as an afterthought. And the other strange thing is that they never use the word graph. They introduce the commuting graph in a sense, but without using the word graph. What they do is they define a metric on a group, and the metric is just the distance in the commuting graph, the number of steps that you have to take where each element commutes with its neighbor in the path. So here's a little example. Here we have two groups, in fact. If you have an abelian group, then everything commutes. So the commuting graph is just a complete graph. So let's take non-abelian groups. Here are the two non-abelian groups of order 8, the dihedral group and the quaternion group. Don't worry too much about the presentations. It happens by some sort of small miracle that these can be written in exactly the same way. I can label the elements consistently with respect to these two presentations. You have to remember that these four elements on the right, in the dihedral group, they all have order 2, but in the quaternion group, they all have order 4. But look at these two red ones. They're joined to everything. They form the center of the group. That's the set of elements joined to everything in the group. Now, here's an application of the commuting graph. Suppose you have somebody gives you a large unknown group. They've given it to you in some way that is unfamiliar. And in analyzing this group, you might want to find representatives of the conjugacy classes. Well, let's just, for an example, suppose that the group they gave you happened to be a symmetric group, but it wasn't given in the usual way that the symmetric group is given. So all the n cycles form a conjugacy class, and that has size n-1 factorial, whereas the transpositions form a conjugacy class of size n times n-1 over 2, so only order n squared. So it's easy to find an n cycle by just picking at random, but if you do that, you're going to wait a very, very long time before you ever see a transposition. Well, this is a lovely idea. I think it goes back to Mark Jerram. If you take the commuting graph and just put a loop at each vertex, because after all, in a group, every element commutes with itself. So you might as well imagine that every element is joined to itself. Now, if you take a random walk on that graph and look at the limiting distribution, you will find that it is uniform not on group elements, but on conjugacy classes. So in other words, the probability of being at some element is inversely proportional to its conjugacy class size. So this blows up the small classes so that they become visible. So for example, if you just look at this picture, the random walk will spend twice as long at each of the red vertices as it will on either of the black, because it has to pass through a red vertex to get between the three wings of this diagram. And I just mentioned that Percy Diaconis and Mariantha Maliaris have used this idea to examine high-dimensional Heisenberg groups over finite fields and argue that there is no simple description of the conjugacy classes in those groups. So it has wider applications. So you might say, well, does the commuting graph determine the group? And of course, you know the answer already because you saw that the dihedral and quaternion groups of order 8 have isomorphic commuting graphs. But there is a relation invented by Philip Hall called isoclinism, which says, roughly speaking, that the commutation structure, the structure of commutators in the two groups is the same. And it's very easy to prove that if you have two groups which are isoclinic in Hall's sense and have the same order, then their commuting graphs are isomorphic. And the reason why the dihedral and quaternion groups work so nicely is that they are isoclinic. I do not know whether the converse is true, whether it's true that the two groups have isomorphic commuting graphs. Clearly they have the same order, but are they isoclinic? Well, I don't know. So I'm coming to the end of my time, so let me just finish up by briefly mentioning that I've talked about the commuting graph, but it's only one of a number of graphs forming a hierarchy, things called the power graph, the non-generating graph, and so forth. And the study of these as a hierarchy has only just begun. They've been studied individually for some time, but we're now starting to look at them as a hierarchy, as each one contained in the next. And there are also other related graphs that have been much studied, the Grunberg-Cayley graph, or prime graph of a group, and the intersection graph of non-trivial proper subgroups that are also part of the story. But we're having a seminar on this in Kochi in India, run by, set up by Ambat Vijayakumar. In fact, I've just been at that seminar. I left it to come here and give my talk at this meeting. So they're probably finished by now, but we found some nice things, and I won't tell you about them now because my time is up, including this strange constant 2.648 and so on. But I think I've said enough for now, so I will stop and thank you for your attention.
Well, thank you very much, Peter, for your most interesting talk. We shall be waiting for your new results. And let's see if anybody would like to ask any questions. I must ask for help because I don't see anything on my chat. Any questions? See? Okay. Okay. João has asked a question, which I'm going to read. Okay?
Hey.
Whenever there is a binary operation, we can define a graph. Does this study happen or can happen all over algebra?
Yes.
No.
Yes, the answer is yes, it definitely can. And I stuck to groups in this talk because I personally find them most interesting. But in particular, I mentioned back here the power graph of a group. You join two elements if one is a power of the other. Now, you don't need very much to define that. All you need is powers to work consistently. So things called power associative magmas have power graphs. And some of the results about power graphs of groups have been extended all the way to general power-associated magnets. Some have been studied to been extended to particular cases like Mufang loops or semigroups, certain kinds of semigroups. But there is quite a lot of work in other parts of algebra, not as much as in groups, I would say, but certainly there are people doing those things and there are interesting results coming up.
Thank you. Any more questions? Let's wait a little bit, see if anybody hides more. No? Well, wait a minute. Okay. Percy says, hi, Peter, you didn't mention perfect graphs.
Perfect graphs?
Yeah.
Yes. Okay, so we heard a bit about perfect graphs in Maria Chernovsky's talk on Monday. There's a particular type of perfect graph, which is comparability graphs of partial orders, which are very much tied into this story because I talked about the power graph here. Well, the power graph is the comparability graph of the partial order and therefore perfect. But they're not in general perfect for the other classes. But that provides you with a very interesting problem. If you take, for example, the commuting graph, for which groups is the commuting graph perfect? The answer is not known. So if you want to get into this topic, there's a question that you could start looking at right away out of the box.
Okay. Any more questions? Okay, no more questions then. So thank you very much, Peter, for your most interesting talk and for leaving us with questions to think about. How someone will be interested in carry on the topic and get in touch with you to discuss these ideas.
Well, I hope so. I hope so. And I do hope to see you face to face before very long.
I hope so.
This is nice, but it's not the real thing.
No, it's not the same. Okay, then we conclude. Goodbye, Peter. Goodbye, Rosemary.
Bye.
Bye. Okay, shall I turn off then?